In this video, I'm going to show you how to find the tangent line to a curve that's defined by parametric equations. Let me just give you a quick review of how parametric equations work by graphing the curve defined by these two. So x is equal to 2t, y is equal to t squared minus 4t, and I want to graph that for t in the interval from negative infinity to infinity. The best way to figure out what the curve is going to look like is to eliminate the parameter t. So to eliminate the parameter t, we'll go to this equation here and solve for t in terms of x. To do that, we'll divide both sides by 2. So we see that t is equal to, instead of writing x of t, I'm just going to write x. And so that's equal to x divided by 2. Then I'm going to take this value of t and plug it into both t's in the equation for y of t. So y of t, once I plug in x divided by 2, it's going to become, instead of a function of x, instead of a function of t, it's going to become a function of x. Okay, so we have y is equal to x over 2 squared minus 4 times t, which is x over 2. So we have, if we multiply this out, x divided by 2 quantity squared is x squared over 2 squared, which is 4, or we can write it as 1/4 x squared. Then minus 4 times x over 2, which is just equal to minus 2x. Okay, so we see that the graph of these two parametric equations is the parabola y equals 1/4 x squared minus 2x. So let's just graph that. Okay, to get the vertex of this parabola, we know that x, the x coordinate of the vertex, is negative b divided by 2 times a. So that's 2 divided by 2 times 1/4, which is 1/2. And 2 divided by 1/2 is 2 times the reciprocal of 1/2, which is 4. So the x-coordinate of the vertex of this parabola is 4. To get the y-coordinate, we just plug the 4 in there. So 1/4 times 4 squared minus 2 times 4. And that is equal to 1/4 times 4 squared. 4 squared is 16. 1/4 times 16 is 4. Minus 2 times 4 is 8. So that's going to be negative 4. So the vertex of this parabola is at the point 4, negative 4. Then to finish graphing this, I'll just find the x-intercepts of this function. To get the x-intercepts of that function, we'll factor it. So we can take out an x there. So we get x times 1/4 x minus 2. So the x-intercepts we get by setting this equal to 0. And so we find that x is 0, or 1/4 x minus 2 is 0. And then 1/4 x minus 2 is equal to 0. We get 1/4 x equals 2. Or x equals 8. So the two intercepts of this are 0. The two x-intercepts are 0 and 8. So I'm going to have to go out a little bit more. So that's 4, 5, 6, 7, 8. So that's my x-axis. Okay, so this right here is the graph of these two parametric equations. All right, what I'd like to do now is find the tangent line to this graph. Okay, so I would like to find the equation of the tangent line to the graph of this function right here at the point that corresponds to t equals 1. Okay, so to find the point that, to do this, first we need to know the point that corresponds to t equals 1. To get that, we just plug 1 into the equation for x and 1 into the equation for y. So we find that x is 2 times 1, or 2. And y is going to be 1 squared minus 4 times 1, which is negative 3. So we're looking for the equation of the tangent line to the graph at the point where x is 2 and y is negative 3. So that's right around there. We're looking for the equation of that line. So we need to know m, its slope, and the point, which we know is the point of tangency to negative 3. To get m, we're going to use the fact that the derivative of this curve at any point gives you the slope of the tangent line at that point. So m is going to be equal to y prime of 2. Well, y is 1/4 x squared minus 2x, so y prime of 2 is going to be the derivative of this evaluated at x equals 2. The derivative of the first piece, 1/4 times x squared. We bring down the 2, and we get 1/4 times 2x, or 1/2 x. So 1/2 x minus the derivative of 2x, which is minus 2. We're going to evaluate that at x equals 2. So that's equal to 1/2 times 2 minus 2. So that's equal to 1 minus 2, or negative 1. So we know the slope of this line is negative 1, and the point on the line is 2, negative 3, so we can find the equation of the tangent line. So y tangent is equal to the slope times x minus the x-coordinate plus the y-coordinate. So that's negative x plus 2 minus 3, or negative x minus 1. Okay, so now we've had a review of parametrics, how they work, and we've seen an example of finding the equation of the tangent line, but that example required us to find y prime. And that required us to eliminate the parameter t. Okay, there's a very cool way for us to completely bypass all of that. Okay, we can actually find the slope of the graph at any point using another formula, and that formula is this. Okay, so the formula, which we'll prove at the end of this video, dy dx is simply equal to the derivative of y with respect to t divided by the derivative of x with respect to t. So in this problem here, we have x is equal to 2t, y is equal to t squared minus 4. And we wanted to find the equation of the tangent line at the point that corresponds to t equals 1. That point was 2, negative 3. Okay, so all we need to find the equation of a tangent line to the graph of any set of parametric equations is this information here. So to get m, the slope of the tangent line, is just equal to dy dt divided by dx dt. dy dt is 2t minus 4. dx dt is the derivative of 2t, or just 2. So if we simplify that, we get t minus 2. So now we know the slope in terms of t. To get the specific slope that we care about, we're going to plug 1 in for t. So our m is 1 minus 2, or negative 1. So now we know the point on the graph. We know the slope of the tangent line. So the equation of the tangent line is negative x minus the x-coordinate plus the y-coordinate, which is exactly what we got when we found the equation of the tangent line by first eliminating the parameter t. Okay, so you have two ways to find the equation of the tangent line defined by parametric equations. It's to use this very nifty formula here, which in fact is what I recommend, or to eliminate the parameter t and use the old methods. Okay, let's do another example using this formula for the slope. Okay, let's find the equation of the tangent line to the graph of the curve defined by these parametric equations at the point that corresponds to t equals pi over 4. Okay, the first thing that we're going to do is find the point that corresponds to t equals pi over 4. The x-coordinate is going to be 4 times the sine of pi over 4. And the y-coordinate is 2 times the cosine of pi over 4. Well, the sine of pi over 4 and the cosine of pi over 4 are both square root of 2 divided by 2. So this is equal to 4 times the square root of 2 over 2, comma 2 times the square root of 2 over 2. So that's equal to 2 root 2, comma root 2. So we want to find the equation of the tangent line to the graph of these parametric equations at the point 2 root 2, comma root 2. So again, the first step was to find the point of tangency. The next step is to find the slope of the graph at that point, and we're going to use this very nifty formula here. So the slope function, m, is going to be the derivative of y with respect to t. The derivative of 2 cosine of t is negative 2 sine of t, divided by the derivative of x with respect to t, dx dt, or, which in this case, the derivative of sine of t is cosine of t, so the derivative of this is 4 cosine of t. So if we simplify this, we get that the slope function in terms of t is negative sine of t divided by 2 cosine of t. All right, now we want the slope at the point where t is equal to pi over 4. So our specific slope is going to be negative sine of pi over 4 over 2 cosine of pi over 4. Okay, so that's negative root 2 over 2 divided by 2 root 2 over 2. So that's the numerator times the reciprocal of the denominator. Let's see, that square root of 2 cancels with that square root of 2, that 2 cancels with that 2. So we're left with a 1 there, a 1 there, and a 1 there. So we have negative 1 over 2. So that's the slope of our curve at the point 2 root 2 comma root 2. So therefore the equation of the tangent line is the slope negative 1/2 times x minus the x-coordinate plus the y-coordinate. Okay, so that's the equation of our tangent line. Okay, so just to review the steps. Step 1, we find the point of tangency. Step 2, we find the slope function using dy dt over dx dt. Step 3, we plug in the value of t to that slope function. That gives us a slope. Step 4, we just form the equation of the tangent line. Okay, let's see where the slope formula comes from. So suppose I have this curve here, which is defined by the parametric equations x of t comma y of t. I want to find the slope of the graph of this at this point x of a comma y of a. So what I do is I find another arbitrary point on the graph called x of t, y of t. Then the way that I get the tangent line is I take this secant line and I let the point x of t, y of t get closer and closer and closer to the point x of a, y of a. Then the slope of the tangent line there is defined to be the limit of the slopes of these secant lines. Okay, so the slope of this tangent line, therefore, is the limit. So sending this point x of t, y of t to the point x of a, y of a is saying take the limit as t approaches a. And then the limit of the slope of that secant line. Well, I know the slope of that is equal to the rise divided by the run. So it's change in y divided by the change in x. So the slope of this tangent line here is the limit of the slope, or is the limit of this as t approaches a. Okay, well, what I'm going to do is I'm going to introduce a t minus a here. So I'm going to go to the numerator and divide it by t minus a. Obviously, I have to do the same to the denominator. So what we have then is the limit as t approaches a of y of t minus y of a divided by t minus a divided by x of t minus x of a divided by t minus a. So since t is going to a, we recognize this numerator as precisely y prime of a, and we recognize this denominator as precisely x prime of a. Okay, so another way of saying y prime of a, that's dy dt evaluated, dy dt, that's dy dt evaluated at t equals a, and x prime of a is really the same thing as dx dt evaluated at x equals a. Okay, so this is why the slope of a parametric is the way I defined it. Okay, so it comes from very much the same place as where we found the limit definition of the derivative.